Light harvesting complex or antenna molecule. Confusing, isn't it? Let's try to understand. This is Dr. Pankaj Kumar, and today we will discuss about the light harvesting complex or antenna molecule that is present in a photosynthesis. So first and foremost things we will discuss that where exactly it is present over there. Okay. So you see, light harvesting complex consists of proteins and chlorophyll molecules, right? And they are embedded in a thylakoid. You can see in the diagram as well. So this is a thylakoidal membrane, you can see there, right? And in this thylakoidal membrane, this is the light harvesting complex, and they are always associated with one photosystem. You know very well, there are two photosystems, what we call photosystem 1 and photosystem 2, and each photosystem has a reaction center. So light harvesting complex is always associated with a one reaction center. You can see in the diagram, the reaction center is P700. Okay. Now, what is the function of light harvesting complex? The function is the transfer of energy to the reaction center. You can see there that how the energy is actually being transferred to the reaction center, right? Now, what exactly is a photosynthetic unit? Photosynthetic unit is consists of 300 molecules, right? And out of 300 molecules, what we see that 240 is a chlorophyll molecule. It can be chlorophyll A, it can be chlorophyll B, right? And second 60 is a accessory pigments, which is also a photosynthetic pigment that is present in any of the photosynthetic unit. Now, the most important thing what we see in case of photosynthesis is that photosynthetic pigment shows the phenomena of phosphorence. Okay, they show the phenomena of phosphorence as well as fluorescence. Now let's try to understand what exactly is a phosphorence and what is its significance. So I am hypothetically taking one molecule. Okay, suppose this is a chlorophyll molecule. Okay, and if I am giving a wavelength of lambda, and if the light is actually coming out and if it is of lambda dash, then if I compare this lambda and lambda 1, then which one is going to be greater? Of course this. So whenever a light is given to one particular molecule and the emitted light is of greater wavelength, then this particular phenomena is actually called as a fluorescence. Now what is phosphorescence? In case of phosphorescence, what happens that if the incident light is taken off, then even for a brief period of time the light will keep on emitting. Okay, so when the light will keep on emitting even for a brief period, even if we just withdraw the incident light, this is what we call phosphorescence. And why it happens? Very simple chemistry. You see, normally you might have read in chemistry that orbitals, the spins of the electrons are anti-spin. That is the normal position. But in case of phosphorescence, what happens? This spin will become the parallel one, like this. Okay. So when we withdraw the light, then it takes extra bit of time in coming to the normal position, and during that bit of time, it keep on emitting the light. Okay. So that is the reason that phosphorescence keep on emitting the light. Now the main question is that where does this phosphorescence and fluorescence operates? You know, fluorescence is going to operates between the antenna molecule and the reaction center, and the phosphorescence is going to operate between the reaction centers and then another molecule that is involved in the Z scheme, which we will be discussing in the subsequent video. So this is about fluorescence and phosphorescence. Now the next question is, how energy is transferred? Energy is transferred by the process called inductive resonance. Have a look at this diagram. You see, these are the accessory pigments, or we can say the molecule that is present in the antenna molecule. Okay. Now what happens? These molecules are in very close association. They vibrate, and during the process of vibrance, they transmit energy. This is what we call inductive resonance. So the energy is always transferred by a process called inductive resonance. Please mind it. Chlorophyll shows the phenomena of fluorescence and phosphorescence, but the process by which energy is transferred, what we call it, is a inductive resonance. Now, another very interesting thing is that the very arrangement of photosynthetic pigment within the photosynthetic unit ensures that there is a one-way transfer of energy from periphery to the center. How? Let's see. Let's take one particular photosynthetic pigment, let it be like this, right, and let it be, it is a reaction center, okay, and here the photosynthetic molecules are arranged according to increasing absorption spectra, okay. So what will happen? Suppose this molecule receives a light of, let it be, say 500 nanometer. Now this shows the phenomena of phosphorescence. What it will do? It will emit a light of greater wavelength. Okay, let it be that it emits a light of, let it be 550 nanometer. So naturally this 550 nanometer will fall in the molecule that is towards the periphery. Let it be this one, the second molecule. Now when this will absorb a 550, what it will do? It will again emit a light of greater wavelength. Let it be 600. Okay, so you can understand in this way what will happen. There is a one-way channelization of energy that is going to happen. So that is the very beauty of this the antenna molecule. So I hope it's pretty clear that the very arrangement of photosynthetic unit ensures the one-way transfer of energy from the periphery to the center. So let's conclude the entire things. In light harvesting complex, what we have discussed, that in thylakoidal membrane there is a chlorophyll molecule, right, and these chlorophyll molecules are associated with different type of photosynthetic pigments, and they ensures the one-way transfer of energy from periphery to the center on account of the increasing absorption spectra.